Assalamualaikum and good morning. Today I will present you about the topic biodegradable and biocompatible polymers for tissue engineering application. I'm Muhammad Abro bin Bazli from section 5. Since so many years ago, tissue damage caused by different causes have drawn the interest of scientists to find a realistic way to handle it. Yes, of course, we are in this technological era, so scientists will produce many alternative way, many the more so many challenge, you know, so nanoscientists suggested some ways, and newest way one is called tissue engineering. They use biodegradable polymers to replace the mesh structure in tissue to make it practical. So tissue engineering strategies are classified into three main components containing scaffold, cells, and biological signaling molecules. Bio Biodegradable polymers are dominant scaffolding materials in tissue engineering field. As you can see in this picture from my left side, so you can see in the blood vessel, you can see here and that you can see the green one, and we call this one is scaffold. Yes, as we can know as the right side too. In construction, we also have scaffold. It is a little bit same thing. You know, we have the ladder, we have the jaringan, and same goes in tissue engineering. Also, we have the same thing here. So here I attach you a YouTube link. So scaffold for tissue engineering applications should be biodegradable, biocompatible, non-toxic, non-mutagenic, and non-immunogenic. And scaffold also have to be produced by synthetic polymers or natural polymers and purely biological molecules. A scaffold is in three-dimensional structure, so you can see in this one, the green one is in 3D structure. So scaffold also must be able to mime the structure of biological function of natural electrocellular matrix. So ECM is a structure support to cells as location for cells migration. If you see the video, you can see the whole process and you will understand it. So this is the process, the schematic of how the process tissue engineering strategy for damaged tissue. So biodegradable polymers have two types of polymers. One is synthetic polymers and second one is natural polymers. And synthetic is compatible with body, biodegradable and absorber. So synthetic polymers also easy change into different 3D matrix structure, 3D matrix structure. And natural polymers is metabolized into metabolites that could be used or it easily removed by kidney clearance, originated from both tissue like collagen and plant like lactic acid. So let's go for about synthetic polymers. Synthetic polymers are human-made polymers. Yes, human-made. They can be classified into four main categories, which is thermoplastic, thermosets, elastomers, and synthetic fibers. They are commonly found in a variety of consumer products. Various main chains and side chains are used to make different synthetic organic polymers. Yes, can be obtained by polymerization of monomers. Synthetic polymers such as polyglycolic acid, polylactic acid, polycaprolactone, polycaprolactone, and so on. Yes, all these polymers is used in tissue engineering science. So let's take a look about the polymer. The first polymer is polyglycolic acid. Okay, so you can see one of the biodegradable. Yes, of course, polyglycolic acid is one of the biodegradable and biocompatible aliphatic polyester. So it is very suitable in tissue engineering. Oh yeah, polyglycolic also we can call it PGA. So PGA can be prepared starting from glycolic acid by ring opening polymerization, tissue engineering scaffold, which are made of PGA. So the molecule structure, as you can see, C2H2O2. And yes, of course, it has N means the polymer. So you can add the sub polymer, add it up, add it up, add it up. So N is a number of you add. So the melting point of the polymer is between 225 to 230 degrees Celsius. So polylactic acid, yes, biodegradable, bioabsorbable thermoplastic. It is group in polylactic acid is in a group thermoplastic and renewable resources. Lactic acid has two optical isomers, which is L and D. So, in medical implant, in form of screw, pins, rods, and orthopedic device. So you can see the melting point of the polylactic is lower than the polyglycolic acid. Okay, it is about 150 to 160, and the molecule structure is C3H4O2. So before this one is about the value of polyglycolic. The carbon is C2, while the polylactic is C3. Okay, so poly and isopropyl acrylamide, so it's hard to pronounce this one, or you can short form is PNIPAAM. Yes, it is thermosensitive polymer. It is synthesized by free radical polymerization and an isopropyl monomers in the presence of the initiator. It has many applications such as biosensor, tissue engineering, and drug delivery. So the melting point is 96 degrees Celsius. So the number of, if you can see, the number of carbon here is 6. Yes, there are 6 number of carbon here. How about natural polymers? Natural polymers is produced by biological system. You can find it at microorganisms, plants, and animals. So the difference from synthetic is human made, but from natural is from the microorganism. So natural polymer has many uses such as adhesive bandage, absorbent, prepare cosmetic, drug delivery and medical scaffolds. So the advantage, natural polymers have its advantage, which is can communicate with biological system, as of course because it comes from the biological, and metabolic compatibility, being non-toxic and low inflammatory reaction, ability to degrade by enzyme, use of hair degradation product in cellular metabolism. But the disadvantage of natural polymers is temperature sensitivity, and natural polymers are destroyed before they reach the melting point, and its complex structure make it difficult to process. So if you can see the example of natural polymers, it have two types. One is polysaccharide and the second one is protein. And you can see the example of each others. So polysaccharide is have three example here: chitin, chitosan, and alginate. And chitin, yes, you can know. We can find chitin at the body of crab, shrimp, or lobster. Yes, if you can see, it's quite hard, right? So that is its chitin. And chitin is basically is white appearance. And chitin also has high strength, biodegradability, and non-toxic. How about chitosan? Chitosan is a derivative of glucan, which is produced by repeated monomers of chitin. Chitosan is chitin, you add it up, chitin, and it will be chitosan. And has features such as biocompatibility, being not toxic, and biodegradability. And chitosan has high blood compatibility and macrophage. And how about the last one is alginate. Alginate is polysaccharide linear, homogeneous, and natural. And alginate mainly in prepared by tar and brown algae. So the other one of natural polymers is protein. Yes, we know protein, and one of the example of protein is collagen. Collagen is a protein found in the extracellular matrix of animals. So if you can see here the structure of collagen here, yes, you can see it. And another example is gelatin. Gelatin is solid substance that is translucent and colorless, obtained from the hydrolysis of collagen inside animal skin and bones. Yes, inside the animal skins and also our bones have gelatin. No wonder, right? So, gelatin from collide and gel in water. Many chemical properties of gelatin are like collagen, and mechanical properties of collagen are temperature dependent. So, gelatin also has many applications in the field of medical science, such as drug delivery system. So you can see the gelatin is primary, there is primary and secondary and also quaternary to me. So that's all from me. Thank you.